Good afternoon, Professor.
Good
Good
afternoon.
afternoon.
Oh, wow. That was awesome. Okay. Good afternoon, Caroline and Savannah and Caitlin. And Savannah's changed her picture also. And Amy. Good afternoon. Oh, good. And Kevin. Oh, sorry, Kevin. I told him it was Kevin. Oh, and Stephen and Amy and Amanda and Estrella. Good afternoon, everybody. And good afternoon, my board. This time my board is and Adan. Good afternoon, Adan. Excuse me. We will get rolling right now. My board is actually resetting. It's a whole new level of annoyance. Good afternoon, Sumaya. Good afternoon, Kevin, Caitlin, Stephen, Amy, Amanda, Estrella, Sumaya, Adan. And yes. Oh, thank you. It's all. Thank you, direct chat person. It actually is all there still. It's not, but thank you. It's very nice. Okay, who else is there? And the board is coming back, I think, I hope. All right, we're gonna get rolling. I'm gonna confirm. I'm just gonna say a couple pieces of information to make sure that it's clear to you. Everything I'm about to say, I think is in Google Classroom. I think you've heard it before, but I want to make sure it's clear. If anything about what I'm about to say is not clear, you're gonna email or text me directly. Hold on, I'm just getting the board. My impression, oh, and here's another person. Okay, hello, Mackenzie. My understanding is that this Wednesday night, no later than 8 p.m., I will post the midterm exam for you. And often it's a little bit earlier than 8 p.m., like 7:15 or something, but no later than 8 p.m., then you're going to turn it back to me no later than 3:05 p.m. next Monday. And again, this is all in Google Classroom, but I just want to make sure we're on the same page here. Or I mean, I believe it's all. And hold on, here goes my board. So it gets posted this Wednesday night. You turn it into me prior to this class meeting on Monday. And then you show up to class. And that's important. And I'm still accepting, I can still accept revisions on homeworks, old homeworks, deadlines on homeworks and homework revisions and updates are loose. They are definitively loose. You're still totally possible to get all the points on any old homework. But I'm saying that to make a contrast clear. Homework, I'm consciously and explicitly loose about timing, but exams, no. The exam, I'm just trying to get this board here. The exam will be turned into me before 3:05 next Monday, and then you'll show up to class. Like that's part of the exam responsibility. You'll show your classmates that you did not take advantage of the situation, that you worked just as hard as they did to get the thing in on time and then show up. And again, that's all saying that's assuming that you have not contacted me. This is okay. That's again all saying if you do have some kind of issue, that's understandable, and you know that you have an issue, then you've contacted me already, or you're going to contact me very soon. Like you're not going to contact me Monday morning, but if you contact me in advance, say, I'm reaching out, I have an issue, I can't get into all the details of it because it's totally personal and blah, 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 but I do have an issue and I don't think I'm going to be able to get the exam in on time for 3:05 p.m., then you and I will work together to make an arrangement if that's what you need, but you'll still show up to class Monday at 3:05. And again, I'm saying this to all of you so that if certain exceptional arrangements are made with certain individuals because they have an individually pressing thing, the rest of you know that just as easily could have been you. It just happens that they reached out this time and they had an issue this time, and maybe this will be you on the final exam, if you know what I mean. I'm just saying, like, I think you get it. So, but unless someone makes an arrangement with me, then they're turning it in 3:05. And just to be clear again, if you didn't reach out to me and your exam doesn't come in at 3:05, then I have an issue and we have an issue. And there are great consequences of that. And it's not a cool thing to do. It's one thing that I will ruffle my feathers. Okay, but no need to be negative about that. That said, so we'll also remind you that the exam is posted 8 p.m. by Wednesday. It's due in Monday by 12:15, by 3:05 p.m. And the one other thing I want to address, because a couple people asked me this question already in texts and emails. Yes, you're allowed to use any resource you want. That's oh yeah. Excuse me. Hold on. Yeah. Okay. You're allowed to use any resource you want to progress in that exam and to learn the material and all of that. Oh, there goes the board again. You're not allowed to use my board as a resource because good luck. You're allowed to use any resource. You're encouraged to use each other to learn and help each other up until the last minute. You're encouraged to be learning this material while you're studying it. All of that. As long as what you write down in the end is only things that you personally understand, and as long as you understand that your job is to show me how deeply you understand them, then we're all on the same page. But one thing someone asked me, or a couple of people asked me, the one resource that won't work for you to use is me. I want to make that clear. Absolutely, as of Wednesday night, once the exam goes out, oh yes, if you think there's an error or something unclear in the exam or something like you don't understand what a question's asking, or you think I might have made an error or something, oh, you definitely can reach out and ask me. You can ask me anything and I won't be offended. But I am telling you right now that unless you're literally saying, I think there's an error here, or I don't understand what you're asking or something, I won't be giving physics answers. And what I really won't do is help. If someone says, I just want you to make sure I'm on the right track so far in part 3 of question 4 or something, I won't do that. There's a number of reasons I can't do that. If that's not fair to other people, et cetera, et cetera. So I won't help you with the exam. But if any doubt in your mind, ask. If you think there might be an ambiguity or an error in the question, ask. And then I'll fix it if so. I won't be offended if you ask, but just please don't be offended if I don't answer something like, can you help me with part 2 or whatever? Okay, that said, and again, the exam will be very, very similar to your practice exam, but it won't be identical. Anywhere that we already went over some kind of solutions or answers in your practice exam in one video or another, or a posted video, then I will change numbers and details. Look out for those changes. They might make an important difference. But all the concepts and the format and all that will be the same. Anywhere that I didn't give you any answer at all or any guidance, then I might leave the question exactly the same. Today, I'll tell you in a minute, today we're going to keep working on one aspect of the exam, of the practice exam. We are going to in about a minute. Is there anything else I'm forgetting now? And I will be around, tomorrow. People come by, but there was one. Well, all right. So I'm going to turn. Oh, something in the chat. Hold on a second. Oh yeah. Okay. So there's a question in direct chat. You definitely have to show work. You want to show a lot of work. You want to show the 5-step method. It is about showing work. The more work, the better. Yes, you're going to show lots of work. I recommend to all of you, again, since this is not about final answers, like in a lot of cases, I already know that you know the final answers. It's about proving how you get to the final answers. It's definitely about showing work. And if the question in direct chat is about how to show that, yeah, the ideal is you write everything out on blank pieces of white paper. You write out all of your solutions, like starting with step 1, the diagram fact pattern, and like label the questions. This is part 1. This is this is question 1, part A, or whatever. And then you start writing diagrams, and then you say what the question is, and then you do a general definition or a principle, and you work it all through, and then you have your final answer boxed, and it's all very clear, everything that you've answered to question 1, part A, or whatever. You're not including copy and pastes of my questions, but you're making the questions absolutely clear. Like, you're writing enough work and enough thorough detail and enough presentation that I can grade your whole exam without looking at the original questions. That is your goal. You don't include the questions, you don't copy and paste them, but you make the questions so clear and so well labeled and organized that I can grade your exam without looking at the original questions. So yeah, you show tons of work, but you do it on blank pieces of paper and then scan them in as one file, compile one file. And hopefully all of you have been practicing this in the homeworks. Like this is all just like one big homework assignment. You compile as one big file, ideally PDF. But yes, Google Doc is fine as well. PDF is really the best, but Google Doc is fine. Word doc is less good. And one big file, and you put it into the Google Classroom, and then I grade it. But yeah, you definitely show work. I was gonna say one other thing about that. Oh, and I recommend, and you'll see in a minute when we get this, again, since this is about presentation, this is about you convincing me that you understand this stuff so well that you can really expand on it and illustrate it and annotate it. And you could use more than one color, and you could do pictures and words and equations and all of this. It's really like a presentation on your part. So therefore, since you have 5 days, since you can work together, since you can use the internet, like think of it that way. Like it's more almost like a research project or something. So the one thing I would highly encourage, one thing that'll make a huge difference is do at least a rough draft with your friends or whatever. Do a rough draft first, and then make sure to give yourself time to do a final copy for this. I mean, it's not a timed exam. It's not that kind of thing where we all understand you're scratching out things under time pressure and like have lots of crossouts and stuff. This should be a final document that went through a messy draft and then landed on a final document. Honestly, like, so I hope that answered the question. Maybe let me know in the thing if that answers the question. So I want to move on and keep giving you some, I'm going to still talk about the practice exam today and some tips and pointers about it. But I want to make sure before I go on, can I just get a show of electronic hands? Is everything I'm saying so far about the exam, is it, okay, thank you, Savannah. Thank you, Estrella. Thank you, Caitlin. Thank you. I didn't even question Kevin, Erica, Estrella, they bounce around. Erica, Mackenzie, thank you. Amanda, thank you. Caitlin, thank you. Katya, thank you. Amy, the other Amy, they're both Amy's. Thank you. Kevin, Sumaya. Okay, so it's clear. I'm assuming it's clear. Okay, cool. All right. And if you do have a question at any point in this, like I'm trying to help with but if you have a question about the practice exam or the procedures, definitely put in the chat. I mean, this is the time. And you still could ask questions this Wednesday as well, but I might be sort of moving on to other material by this Wednesday. But certainly, so Mackenzie and Rashma, do you have a question, or you still have your hand up from a moment ago, or do you have a question? Okay. All right. So here's what I'm going to do now. Sorry. I want to make this as clear as possible. This equation, there goes my board again. I don't know why. I know you explained it to me. I know. Okay. What we're going to do now, I mean, that equation that you just saw that just flashed before your eyes, that's where I'm heading with this. But I want to make clear the equation at the top, of this board right now, like above the red squiggle line, that equation, in effect, is the punchline of your response to question 4 in this exam, or part 4 in this exam. Okay, I kind of walked you through, I like to think I walked you through sort of parts 1 and 2, I think it was, of the exam. I didn't do everything, but in one of the recent class videos, I walked through, if not the trees, the forest of parts 1 and 2, right? And then I alerted you that a very detailed walkthrough of part 3, the pendulum, is done on a video to another class section, and that's posted in your Google Classroom. It's called like pendulum part or something. So I feel that there's a lot of material out there for you. And in fact, I think I also even posted a separate solution or solution bits that are similar to problem 1 or problem 2 or something. So I think you have a lot of material on parts 1, 2, and 3. Again, I encourage you to talk with each other, straighten it out. Look out for slight differences look out for differences in detail when you get the actual exam. and be wary of them. But question four is where I'm focusing my attention today. In what I feel is that question four is the most open-ended. It's the most kind of like free response part of this exam, right? It's like a free response. Like you have to explain, you have to put forth a big sort of synthesis of a concept. The concept is how we make wave motion out of a bunch of oscillators. That's the concept, is how a bunch of oscillators together, arranged in a very specific way, make wave motion, right? That's the larger concept. I'm asking you in question four to break that down very thoroughly and very authentically in terms of math equations, diagrams, English explanations. Like you really want to give me like a full presentation of how wave motion is composed of carefully arranged oscillators. Now, what I feel is that I really did give you the broad strokes of that in the most recent class video. It's posted, but the most recent class is where I really went, I think, to the core of that. And you want to watch that, and I'm giving you all the information. There's no mystery about what the information is, but I'm asking you to understand the information and show me that you understand it. So the last video is a good one to watch, but now what I'm going to do now is break it down even further, or give you like more. I'm going to assume now that you sort of watched that you were part of the last class, that you sort of get the big picture, that, and now I'm going to try to break it down further. If you put this class together with the last class, all of it together is what you really need to do an optimum version of question four on the exam. So in the last class, we said, well, yeah, okay. So I'm going to say a lot now. I'm going to say a lot about this page. There's a lot going on this page. I'm going to explain it in a lot of English. I do suggest you take notes. I'm going to say a lot of things that I can't fit in writing on this page that I feel that were written down in the last class, but I'm sort of relying on you to realize that I've said them already. You're going to have to sort of go back and forth. But so if I go too fast for anybody today, take it as a reminder of what you need to know. Don't try to learn from what I'm saying right now. Take it as you get my point. So here's what I'm saying. This equation on the top of the page is what describes the following arrangement. I'm going to say it a couple times in English. This equation at the top of the page is a vast collection of identical vertical oscillators arranged equidistantly along a horizontal axis of space, but staggered in phase by a constant step. I'm going to say that one more time. Hold on a minute. Okay. This equation at the top, ultimately, you're going to show you're going to draw diagrams and use English and label things. And you're going to do a series of equations that together in the end land on this equation. You're going to show me, so I'm not going to say it again in English, that if you take a huge collection of identical vertical oscillators and you arrange them uniformly or equidistantly along an x-axis of space, and you stagger the oscillators in phase by a constant step or a constant amount, then you will have an arrangement that can be captured all at once by this equation at the top. I'm going to expand more on this again, but the overall summary is this equation at the top describes a vast collection of identical vertical oscillators arranged uniformly in horizontal space, staggered in phase by a constant amount. Now, again, if you didn't get, okay, I'm going to keep sort of saying it different ways, and I'm going to try to break that down, but that's the point. Again, even if you don't fully understand that right now, and you really might not, and by the way, that's okay. In fact, it's not a bad thing if you don't fully yet understand what I'm saying. What would be a bad thing is if you pretend to yourself that you understand it when you don't. It's perfectly fine for you to admit that you don't get this yet. And that's why I'm just telling you what you want to get, and you want to rewatch the last video and rewatch this one. What you're trying to get is what I just said. Well, and some more things as well. You're trying to get it. It's not a problem if you don't get it yet. It's a problem if you don't know what it is that you're trying to get. And it's a problem if you kid yourself into thinking you get it when you don't. Now, so first of all, I'm going to, when I say a vast collection of identical vertical oscillators, by identical, what I mean is each vertical oscillator, each mass on a vertical spring, let's say, right? Each mass on a vertical spring, I'm believing has the same mass in kilograms on the spring and the same stiffness of spring K. So when I say they're identical, I mean they have the same, all of them have the same M and the same K. Therefore, all of them, and this is something you would want to explain in your question for, if they're all identical, they all have the same M and they all have the same K, therefore they all have the same omega. So omega equals square root of K over M, which is something you show earlier in the exam in like part 3 or part 2 or something, or both. So I'm saying now, first of all, you draw a bunch of masses on vertical springs, all laid out horizontally. Again, the diagram for that is in a prior video. You can check it out again, but I'm asking you in your way to draw a bunch of vertical springs with masses on top of them, and each one is labeled K and each mass is labeled M. And you could further assume or say that each one, because they're identical, they're each going to be set to have the same amplitude, like they're each going to be pulled down to the same initial displacement from equilibrium. So you got all these vertical oscillators that are all the same in terms of their intrinsic properties and their configuration constant. And they're all spread out equally in space. So maybe the very zeroth oscillator is right there on the zeroth edge of some meter stick. And then the first oscillator is at 1 centimeter away. And then the second oscillator is 2 centimeters away. It's at, like, start with 0, big trick, big tip, pro tip, start with 0, don't start with 1. So 0, 1, 2, 3, 4, right? So you got these oscillators drawn out on a horizontal axis, and each one is free to oscillate vertically along a y-axis, right? And each one has an oscillating angular frequency of omega and an amplitude of A. But they're all staggered in phase by a constant amount. What do I mean by that? I mean, and you're going to show me in your picture, just like we did in the last class, you're going to show me what it means to be staggered in phase by a constant amount. For example, like the example I used is, let's say, example, the constant phase step, the constant amount of phase staggering, let's say, for example, is pi over 2 radians. For example, pi over 2 radians. Well, pi over 2 radians means a quarter of a cycle, because there's 2 pi radians in every one cycle. Something for you to explain, right? But pi over 2 radians would mean a quarter of a cycle. A full cycle is all the way there from one amplitude to the negative amplitude all the way back. That would be a full cycle, right? So a half a cycle would be all the way from one amplitude position to the other amplitude position. And a quarter of a cycle would mean, for example, from one amplitude position to the equilibrium, to midway point, to the center, right? So if they're staggered in phase by a constant amount, it would mean that every next centimeter, that every oscillator is one more pi over 2 radians into its phase. One for every next centimeter in this arrangement, or meter, whatever. For every next oscillator in this arrangement, there's a gain of a quarter cycle in the phase. So, for example, what that would mean in a picture is, like, if the first oscillator, if when time equals 0, the first oscillator is at as far down as it could possibly be, at that moment, the next oscillator is at the equilibrium point, and the next oscillator is as high up as it could possibly be. And then the next oscillator is at the equilibrium point, and then the next oscillator is at the lowest. If the phase step is pi over 2 radians per every meter. That's an example, right? So you would draw all this out. And each oscillator, therefore, so all the oscillators are doing the same thing. They're doing the same cycling rate, but they're all staggered. They're all at different places doing it, right? That's what you're trying to make an alternating pattern of these patterns, right? And so then you would write down a separate equation for each one. You would say, so therefore, for example, this 0th oscillator would have an equation to describe it like y equals a cosine omega t plus 0. Whereas the first, like the next oscillator, oscillator number 1, would have an equation like y1 equals a cosine omega t plus 1 times pi over 2, for example. And then the next, right, because it's out of phase by pi over 2. But then the next one is out of phase from that by pi over 2. So it's 2 pi over 2s out of phase with the original 0th one. So the next equation would be like y equals a cosine omega t plus 2 pi over 2, which is the same thing as pi, right? And so you'd write down a different individual equation for each oscillator. Now, again, I'm saying this maybe a little bit quickly, and maybe it's a little bit abstract for me to be saying this now without me drawing it. But please note again, we did draw it. If you go back to the last class video, we did all this, and this is what I'm asking you to give back to me. I'm asking you to give it back to me. And so you would write down an individual equation for each one of these individual oscillators. And all this, you're using notice I've given you one big sentence that's long in English, and I've given you a couple of times here. I'm taking the words very carefully. I'm saying words that I think say the concept and hopefully say it to you. I'm not asking you to mirror back my exact words. I'm saying my words enough times so that you get the idea, so that you can give me words of yours that work to the same idea, right? And same thing with the diagrams and all of this. I want you to give me back all this information, but in your way. But here's the skeleton that you got to follow. So each one of the oscillators has its own equation, right? And so like if you take like the 7th oscillator that's at the 7 meter mark or the 7 centimeter mark, its equation would be, for example, like y equals a cosine omega t plus 7 pi over 2. But now pi over 2 is just the example that I've been using because I think it's a particularly vivid example of the phase step. If you really want to show me that you really understand this, one of the best strategies you could follow is give me all these diagrams and give me what I'm saying, but try a different example. If you really want to prove to yourself that you understand this and prove to me, instead of you doing pi over 2, do something like pi over 4. Or pi over 3, or pi, or something, and draw it for that. I mean, if you come up with your own example, that's the best way to demonstrate that you really get this. But so each one of them has its own equation, but then you step back and realize, okay, whether we use pi over 2 as an example, or pi over 3, or pi over 4, what that is, that's the number of extra radians into the phase that we add for every meter that we walk over this whole arrangement, right? Whatever number you pick, pi over 2 or pi over 3, it's measured in radians per meter. It's the extra amount of radians in the cycle, that it's the extra amount of phase shift that you're getting per each extra bit of displacement that you walk along the x-axis of this arrangement. So that's what we mean by K, right? Omega is the rate in time at which each one of these oscillators goes up and down. K is the rate in space at by which we keep adding chunks of phase for each meter that we walk horizontally. So omega is measured in radians per second. K is measured in radians per meter. And we get, and therefore, okay, how can I, let me pause for a second. Yeah, I mean, so omega is, and I'm going to get to the rest of this sheet in a second, but omega is angular frequency, radians per second. That measures what's happening for each individual oscillator. K is angular wave number, number of radians per each meter that you go horizontally. when I say you're trying to explain all this and finally land at that equation at the top, you've got a couple of jobs. One is, for sure, you want to define, by the time I'm done reading your thing, I don't just want to see that equation. I want to see that equation and have clear explanation somewhere in there for what each of the terms in that equation actually means. Like, what's its units? Is it an independent variable? Is it a dependent variable? Is it a constant, etc.? So you are trying to build up and develop that equation as an explanation for a horizontal collection of vertical identical oscillators staggered in phase by a constant step, right? That's what you're trying to show. But now, before I go any further, like, why do we care so much about this? What's the point? Yes, one of your big goals is to show that that equation describes a collection of oscillators. But the real punchline, the real reason we care about all this, and this is something you have to develop also in your answer to question 4, is that if you stand back and look, and again, I'm talking in English now. Hopefully this was written down in the board in our last class, and hopefully you're writing this down right now. But what I'm about to say is just as important to your answer as anything else I'm saying. That the reason we care about this equation and the reason we care about a collection of phase staggered oscillators is that if you step back and then look at what you've produced when you put together a collection of phase staggered oscillators, the point is that this creates wave motion, that we will see a pulse ripple across this collection along the horizontal axis. You'll see a bump or a crest or a trough. I mean, you'll see all of those things, but whatever is easiest for you to picture. If you do this, if I go up and then down, and the next massive spin goes up and then down, and the next goes up and down, it is like a bunch of human beings in Yankee Stadium. I mean, that's literally what it is, right? Or whatever state. It's a bunch of human beings going up and then down and up and then down and then up and then. And if you stand back and look, what do you see? You see a ripple go through those people, right? And if you do this, for example, in lab 3, if a bit of spring goes up and then down, and then the next bit of a long metal string, if a bit goes up and then down, and then the next bit goes up and then down, and the next bit goes up and then down, what you see is upness, a bump, a crest, move horizontally from one lab partner to the next. Now, this is huge. I'm going to go crazy on this right now. Again, I'm going to go get a little dramatic, probably more than I should in a minute. But this is the thing, and I'm going to be in English now. But you are going to explain this to me in question 4. After you've walked through all these individual equations, and then you've put them together to make one big equation, and you show how this one equation describes a collection of phase staggered oscillators, then your point is, well, the point of this is that this collection of phase staggered oscillators now creates a ripple or a pulse or a disturbance or a crest, whatever you want, some word like that. It creates something that now propagates, that moves. Propagate means move. By arranging all of these individual particular thingy things that are all oscillating along vertical axes within their little defined specific neighborhoods, we've now created some entity that will move, not oscillate, move, propagate, like flow. That's another great word. We've created an entity that will now flow horizontally. That entity is like a bump or a trough. It's some kind of disturbance, some kind of distortion, some kind of identifiable shape in the large collection of oscillators, some shape. And I do mean shape, like you'll see a bump, right? Or you'll see a valley. Travel along horizontally through these oscillators, and it will travel a defined amount, it will travel an observable, measurable amount of space, in an observable, measurable, reproducible amount of time, and therefore it will travel at some calculable, analyzable, predictable speed, right? Space per time is speed. So we've created some kind of entity, some kind of disturbance, some kind of bump or pulse that will flow horizontally throughout this collection of oscillators. The collection of oscillators we can call a medium. Through this medium, this collection of particular identifiable thingy things, we've created something that will move in every scientifically verifiable way possible. It will move horizontally and pass all of the scientific tests of real, actual, predictable motion, right? But here's the key again. I'm going to say it again. And once you get it, and then you're just trying to get it back to me. But until you get it, you don't get it. And when you don't get it, you might think you get it. But you'll know you get it when you think for a minute, I don't get it. And then you realize, oh, I get it. What's the it? The it is, if you do this with a bunch of little pieces of mass on metal, if you set up a bunch of little coils of metal and have them go up, like up, like that, if all them, you'll create something that flows through the metal horizontally from point A, say lab partner number 1, to point B, lab partner number 2. You'll create something that moves horizontally, in this case, from point A to point B. And all that is doing any kind of motion at all is metal. All that's doing the motion, everything that's doing motion is metal, in this case, of like springs going up now, right? I'm going to say this again. You've created something that moves horizontally from point A to point B, and all that is moving is metal, but this is the key but, if anybody's still listening with me, which I pray, the key but is there's no piece of metal at all that moves from point A to point B. From, again, shake a long thing of metal with your lab partner. You will create a disturbance in that metal that will flow from you to your lab partner. You'll have motion from point A to point B, and all that's doing any kind of moving is metal, but there will be no metal that you can point to. No piece of metal literally makes the journey from point A to point B. So what you've created is immaterial motion. It's real motion. Something's moving. There is motion, but there is no thing doing that motion. Like, that is that's crazy. Once you get it, you'll know you get it if for 1 minute you think you don't. If like for 1 moment you're like, wait, is that what that's not, oh, that is what he means. Like, I really am saying, and I'm not trying to confuse you, and I'm not trying to say that I'm not trying to be overexcited about it, but I just am overexcited about it every time I think about it. 3 times a day, week after week, for 30 years. Like, I still can't, and you'll know once you get what it is I'm trying to say, but I'm saying we're putting together a bunch of material objects and asking them to move in such a patterned way that the motion we end up getting is not material. In fact, okay, hold on. So I'm going to say it one more time. What is wave motion? What is wave motion? Wave motion from point A to point B is motion from point A to point B for which no individual or particular or material or countable or discrete or separable or massive or identifiable object actually ever goes from point A to point B. That's what wave motion is. Wave motion from location A to location B is a motion that is real, for which there is no real mover. I will say it one more time. Wave motion from here to there means something moves from here to there, but no individual thing moves from here to there. I'm not trying to be cheeky or cute. In better, more technical language, I'm saying wave motion from A to B means there is motion from A to B, but there's no particle. There's no particular entity. There's no piece of mass that goes from A to B, but something goes to A to B. It's just not mass. It's just not particles. It's just not stuff. What is it actually? I would say it's information. You could say it's energy, but I think that's a cop out. I think what's going from A to B is information. It's something, but it's not, it's something that matters, but it's not matter. Now, wait, I'm going to pause. And this is what, okay, I'm going to pause. I'm going to move on again in a second. But this is what I want you, and you see, it's an abstract concept. It's a very real concept. It's a major transition in science that we are now. One of the reasons all the math we've been doing seems so abstract is because we're actually now finally trying to analyze motions through the material world that themselves are not material. It is abstract. Abstract doesn't have to mean hard. I'm not saying it has to be difficult. It might be, it might not be. I'm just saying it's removed one step from concrete, tangible reality. That's why it excites me. But your job in this free response question 4 is to show us how we make immaterial, or how nature makes immaterial motions from a group of highly organized material motions. That's what this is all about. And so if you put a bunch of if you have a bunch of cosinusoidal oscillations in time, all organized in a cosinusoidal oscillation in space, those two things together make wave motion. One oscillation is not a wave. Many oscillations is not a wave, but time oscillations but harmonic time oscillations organized harmonically in space, that makes a wave. That's why the rest of the exam, all 3 other questions are all about, do we really understand harmonic oscillation? Do we really understand harmonic oscillation? Harmonic oscillation, harmonic oscillation. When we finally get harmonic oscillation in time, we stretch it out in space, and now we have immaterial motion, and that's the point. Now, I'm still going to go on. I mean, actually, I'm going to check in for a second. Like, I know I'm talking a lot. Oh, cool. I just got something in the chat. Great. I was just about to ask. Okay, hold on. Let me see. Oh, great question. Okay. Now I'm going to answer this a couple. All right, I'm just going to I'm not going to say the person's name. I'm just going to read the person's question. Great question. So someone's saying in the direct chat, and by the way, this would be a good moment for anybody and everybody. If you don't understand, or if you have any thoughts about what I'm saying, you might want to put them in the chat now, because this is a big deal, and it is a free response question. Like, I'm trying to give you the answer. Okay, I want to answer this direct chat thing, but also please notice, I'm literally telling you the answer, but it's not cheating. I'm telling you the answer because the answer is hard enough and deep enough that I need to see on this exam that you get the answer. So that's why you're free writing it yourself. You see, like, you take the answer seriously. I want equations. I want drawings. I want English. You're trying to get to the punchline of how mathematically we put together a bunch of oscillations to make a wave. Now, in the direct chat, someone says, so instead of the mass on the spring, is the person moving the spring the mass causing the oscillation? That's a great question. Sort of yes and sort of no. Well, it's certainly true that if you hold a long string, so I'll repeat the question, is the person moving the spring the mass causing the oscillation? Well, if you're holding a long string and I'm with your lab partner and you're at opposite ends, certainly who's ever shaking it up and down, yes, they're the one causing the oscillation, yes. But the mass is still the little bits of mass in the spring itself. Like, here's what I want to say. This is all really what we're doing here in question 4. We're doing lab 3 backwards in a way. And by the way, the person is very right in direct chat to think, okay, Yavram seems to be saying like we've gone from oscillation to waves. And that's right. We've gone from oscillation to waves. And the person in direct chat is sort of asking, well, so what takes the place of our old concepts? The mass that we used to have going up and down is still a mass going up and down. What it is a bit of it's still a mass going up and down. It's a bit of that long coiled metal long spring that you and your partner were holding. Notice when you did lab 3, if you made these pulses going back and forth and you made a big movie of them, so you made a wave. Like here, what I'm trying to say is how we built up a wave from oscillations. In lab 3, you looked at a wave, and what you're really trying to show yourself is that if you break apart a wave into different pieces of analysis, you'll see different oscillations acting as pieces coming together to make this wave. So in lab 3, what you did, so I think hopefully this will answer the person's question. I'll ask her or him, we get to check in and tell me if I'm answering it or not. But in lab 3, you have these pulses going back and forth between one lab partner and another. You have a movie of it. And then you broke the movie down into 2 separate analyses. The first analysis was you said, let me pick a horizontal spot. Let me pick a position and fix it in my mind. Like, let me just look over there where there's a meter stick in the movie. Like, let me look at this part of the movie where there's a meter stick sitting up and down, and I'm just going to watch the spring where it intersects with that meter stick up and down. I'm not going to look at any of the rest. I'm just going to look at that horizontal spot, right? So so you looked along some reference line, like a meter stick that was in your movie, and wherever the metal of the spring was, you put a red dot, right? And then because you had a box unchecked in the settings of the movie settings, because you unchecked the box that said allow multiple points per frame, as soon as you put a red dot there, the frame of the movie advanced. So now the spring was up a little higher. The little piece of that spring on that horizontal spot was a little bit higher. So you put a new red dot. And you kept fixing on that one horizontal place. I'm going like this. That's not hard, but I'm saying at that one, anywhere along this line, you're at one horizontal coordinate. So you put a red dot, the frame advanced. So then in the next unit of time, you saw where the spring now was, what the height of it was, and you put a new red dot, and you kept doing that and doing that. So what you were analyzing there, you were analyzing, if I just hold X to be constant, what is the height of the spring doing as a function of T? So you were tracking with those red dots how high and low that section of spring was going up and down. That section of spring that you were tracking at a given X position, that was the mass. That mass is acting like, is being a harmonic oscillator going up and down, up and down. If you had looked next to it, you would see a different piece of mass going up and down, and you'd find probably that it was the same rate, just out of phase with the first one. Like, well, this one's up, that one's down or something, right? So the mass is that bit of spring that you're watching go up and down. And indeed, if you make a graph of it, so the first graph on this page, the graph in the center of the page here, the graph shows that if y is a function of time, if you're tracking what y is doing as a function of time, it's going up and down smoothly, cosinusoidally. It's a harmonic oscillator. If you just focus on one slice of this whole movie, you've got a vertical oscillator, a mass going up and down. So that's your mass right there. The amount of time between any 2 peaks, any 2 amplitude positions, or the amount of time for a full cycle, we call capital T, the period of time for one cycle. It's measured in seconds, right? So in the brown, okay. So that makes sense. Oh, okay, great. Thank you so much. That's like a lot more points that you, thank you. Okay, cool. I'm not going to keep going now, but cool. So the period of time is the interval between those 2 peaks on a time graph. Right now, that's just, that alone is oscillation, right? Anything you understand about that time graph, anything you, and omega is 2 pi over that T, right? It's like, it's the reciprocal of that T, but multiplied by the conversion factor of 2 pi, because there's 2 pi radians per every cycle. So that top graph, I mean, the graph in the middle of the page, and that statement about omega, that's everything that you once upon a time, or in the last 3 problems of the exam, all understood about angular frequency, and you understood about individual harmonic oscillators. Now, the catch of lab 3, like the new information of lab 3 and lab 4 and of this, is that that's not all that was going on. That's what you found. If you focused on one particular X value, you saw harmonic oscillation expressed in Y as a function of T. For one constant X value, Y was harmonically oscillating as a function of T. But then you had this other option. Like that was a slice. That was a physical slice of your overall movie. You also went to this other option where you said, you know what, now I'm going to take a different type of slice from my movie. I'm just going to take a frame. I'm going to look at a frame. I'm going to back up and I'm going to say, I'm going to hold time constant. Now I'm looking at the bottom graph. You hold time constant and you say, what if I just picture one moment? I consider one point in time. And now I put a dot wherever the metal spring, wherever the height of the metal spring is, like way over here, I put a red dot, but I check that box in the movie functions of Logger Pro or whatever, where it says, yes, please allow multiple points per frame. So I put a red dot where the metal spring is, but now the frame doesn't advance. So I'm still in the same frame. I'm still looking at the same unit of time. Instead, I let my eyes gaze over and I go to a new value of X. Right? Before I didn't do that. Now I'm saying, let me change X. Let me walk over a millimeter or whatever and see how high the spring is there. Oh, it's a little bit higher. I put a red dot there. Then I let my eyes gaze a little bit farther along the X axis. Where's the spring now? Oh, it's over there. I put a red dot above there. Right? So now what you're doing is you're tracking what is Y doing as a function of X for one given value of T. And lo and behold, you get a cosine graph again. Right? This is what I'm saying, that Y is some cosinusoidal oscillation in T. That's not a wave. That's oscillation. Y is some cosinusoidal oscillation in X. That's not a wave. That's just a static picture of a wiggle. But put these two things together, have a static picture of a wiggle moving up and down. Or have something like this next to something like this, next to something like this. Then you have a wave. That's what you're trying to, so what you're trying to explain, all the stuff before these graphs, you're trying to say, if you stagger time oscillations in space, if you have time cosines spread out in a space cosine, then you have a wave pulse. That's what we're trying to say. It's really deep. I mean, it's once you get it, you get it. But until you get it, it's like a lot of craziness. So what is K? So let me back. So pro tip here. Okay, Well, yeah. Let me say, this is not to test whether you understand what was going on in lab 3 when you did lab 3. If you're like any normal person, including me, you didn't understand what was going on in lab 3 when you were doing lab 3. I know that. You're not trying to fool me, and I'm not trying to fool you into thinking that we understood this weeks ago and now we're spitting it out. No, we did it weeks ago. Now we're trying to make sense of it. I'm trying to show you that now, in retrospect, with stuff that you were doing in lab 3 was trying to say this. It was trying to say that oscillations in time oscillating in space together make a wave. And here's the thing. Here's the pro tip. When I'm grading these things, question 4, I'll tell you right now what I like flip immediately to see. I mean, I look to see if there's diagrams. I look to see if there's English. I look to see if there's math. And there usually is, because people at the very minimum like copy down the diagrams and the equations from these videos and from my notes. I know that. But how I know whether someone's actually trying to make sense of this on their own or not, how I know if someone actually gets the question and is really trying to answer it, is the people that get to an explanation of K. Because omega, when you were doing lab 3, if you recall, when you were doing lab 3, you had just barely started to understand omega at that time. And I don't mean that shamefully. Like, that's just the reality. We had just barely introduced omega into our lives. We were just barely starting to see what angular frequency meant. Then all of a sudden in lab 3, there's this K thing. Now what K is to space as omega is to time. K is what turns oscillators into a wave. K is called angular wave number for a reason. K is the thing that gives people the most trouble in lab 3. It gives people so much trouble that a lot of people don't even admit to themselves they don't get it. They just ignore it because it's so new and so out of left field. I know that. But by now, what I want you to start seeing as you're putting this together is what K, first of all, I'm saying the more you explain K, the more you define K as angular wave number, the more you show me that it is radians per meter, the more you show me that on this graph at the bottom of the page, where we hold T constant and we look at Y as a function of X, if you show me that the space between the interval between two peaks on the space graph is no longer period, it's no longer capital T, because now we're looking at space. Now we're looking at the length between two cycles. That's no longer t, the period. That's the length of the wave in space. It's called wavelength. And the Greek letter that we generally use for it, and you have in other classes, and you have in 7th grade maybe, is a lowercase lambda, the thing highlighted here. And if you're hearing this for the first time now by me, then I'm telling you, that thing that's highlighted is called a lambda. It stands for wavelength. It is just that, the length in space measured in meters of a cycle, as opposed to t, which is the duration in time of a cycle measured in seconds, but they're totally analogous to each other. Lambda is to space as t is to time, and k is to lambda as omega is to t. If you can show me that you understand that, you're really showing me something. The more time you spend explaining to me what k is by analogies to omega, the more I see that you see the distinction between an oscillation and a wave. All oscillations have omegas. Only waves have k's. What is k? I'm going to give you one last pro tip of how you can explain k. Like, I think there's a lot of k is the thing, and you have to explain it. You can't just copy what I'm saying here. Believe me, I know the difference. Another way you can explain k, and this goes back to the other lecture, it's in the video, k is that step, right? It's how many radians of extra you're getting per every meter. K times x together make phi, right? One given oscillator can have a phi. It can be a phi of equal to 0, meaning it started at an amplitude position, or it could start with a phi of pi over 2, meaning it started like a quarter of a cycle of the way into its motion. Any individual oscillator can have a phi added to the omega t. But what we're saying here for a wave is phi is no longer just a fixed number. Phi is now equal to kx. Phi itself is a function of space. Phi is equal to kx. And you could write this down. I mean, I did in the last, I'm not writing it for you now, but if you do this, it's major kudos to you. Phi equals kx. In the case of a wave. Therefore, by definition, what k is phi divided by x. I mean, phi is kx. Yeah, so k is phi divided by x, meaning what k is the amount of extra phase per every unit of space, like pi over 2 radians for every meter. Meaning you could make a little graph. If you really want to blow me away, you could make the little graph that I made last class, where you put x on this axis and you put phi on this axis, and you draw a straight line with y-intercept 0, and you show that the slope of that line, the rate at which phi increases as a function of x, that's what k is. K is the slope of the phi x. That's an individual graph. I'm just saying to make a point. K is how much the phase, it's the step. When we keep saying staggered in phase by a constant step, the step is k. And it's called the angular wave number, because once there's a k involved, now a bunch of oscillators together have made a wave. Now I'm going to go on, but that your job is to try to spit the, but I'm saying one last time as a pro tip, you'll know you've really answered this question if you can build up that equation at the top of this page, build it up from a collection of phase-staggered oscillators, show that that's a collection of phase-staggered oscillators, and then show how that actually is ultimately wave motion, and you'll seal the deal. The more you analyze what exactly k means in all of this, that I swear anybody who's not listening now, what they're going to do is they're going to copy a lot of stuff, and they're not going to say anything about k, and they're going to lose like a lot of points. Like that. I mean, hopefully that's not any of you listening right now. Just explain k a lot, and that's the first thing I'm going to look for. But now, just to summarize, I know we're right. We got 15 minutes left. And I'm going to tell you also right now, we've got 15 minutes late. I think this is all, hopefully this is all helpful. I'm not trying to yell out of anger. I know that 4 is the most open-ended, and it is also kind of the most important in a way to me to see where we are in this course. So I'm trying to give you as much help as I can with 4. I'm going to tell you right now, I did the same lecture in the other class period this morning. I got to the end of where I wanted to get. I think it was clear. I mean, for me, I think I landed where I wanted to. In case we get cut off or you get cut off or anything, I want to tell you right now, check out the video from the other class, because it definitely gets all the way through what it is I'm about to say. I mean, I think we will as well, but if it gets fuzzy for just, I do things slightly, whatever, you get my point. So Here's a summary of what I'm saying right here again. This is a summary of what you're trying to cover in question 4. Y equals A cosine omega t plus kx is a collection of phase staggered oscillators. Now, I just starred that in red because I'm giving you the forest here. I'm giving you the roadmap. For those of you who are still like listening to me, the benefit of this is I'm telling you that's the summary of what you're trying to give me. But if you just literally, anybody who's not listening now and just going to copy this, if you literally just wrote that, it would not be sufficient. And in fact, it would flag that you're just kidding yourself. Like, you can't just write a collection of phase staggered oscillators. You have to write like a collection of identical vertical oscillators staggered in step by a constant amount, blah, 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 right? I mean, staggered in phase by a constant step, blah, blah, blah. That's why I put a star there, right? And that's why it says that you must expand. But here's the summary. You're showing me that that equation is a collection of phase staggered oscillators, yet that equation is also wave motion. Thus, wave motion can be made from a collection of phase staggered oscillators. That's your goal, to show me in question 4 that you get how wave motion is a collection of staggered oscillators. But that wouldn't be interesting unless you also show me what you mean by wave motion. Wave motion itself is motion from here to there for which no individual particle actually goes from here to there. That's our point. Okay, now I'm going to move on. And again, you can watch all this. I'm moving on. I'm going to say everything I say now is still related to this. Everything I say now is still related. And anything and everything you get out of what I say now will definitely help your question 4. And it's going to move our material forward in this class, everything I'm about to say now. But I'll also say, to be honest, if you can nail everything I just said, and you don't quite get up to this bit that now I'm going to, you could still probably get full credit on question 4. Like, we've now closed the door on what would constitute full credit. Everything else hopefully will help you now and will help you for the rest of the class. But it's not, but it's like, okay, I don't know how to make that any clearer, but everything I say now for the next 13 minutes will help you with question 4, but where you need to get to was up until the last page. Okay, this is where you need, okay. And I'm going to say one last thing too. Obviously, I think question 4 is important. Obviously, I'm trying to give you as much help as I can. Since I really recommend that you do a rough draft and then a final draft of this exam, I would recommend some of you, if you think you get question 4, do it first. Or if you're not sure, do it first. And any of you who feels like you're starting to figure things out while you're doing it for the first time, please understand that that's the point of a physics exam. If you feel like you're just starting to get this for the first time while you're doing this exam, that is not cheating. And that is not something to be ashamed of. That is actually how physics exams work. They are not to find out what you did get. They're to get you to get it. Sometimes we don't get this stuff until we're forced to put it all together. So please view the test that way, as an opportunity to put this all together. So if you start working on question 4, even before you fully know what you're doing, and then you start seeing things, great. And if you end up going to town on question 4 and have a whole big, beautiful thing with diagrams and words, then you could staple that on top and put all the rest on the bottom. As long as you're clear, this is question 4 first, as long as it's clear what I'm looking at. If you think you're going to blow me away with question 4, and then that'll help bias me toward you for the rest of your exam, by all means, do that. Anyway, I'm now going to ask, what happens if we take derivatives, if we consider instantaneous rates of change of the different functions of this wave in the manner of lab 3? Because here's what we're really saying. If you really understand everything we just said, we're saying that a wave is a function of 2 independent variables. Height depends on vertical position, depends on horizontal position, and independently time. It's 2 functions. That's why it's 2 graphs, right? So what if we try to separate this information the way you did in lab 3, and we look at the rates of change for each function? Can we do that? Yes, we can. This is called looking at this is called taking derivatives of a multivariable function. We now, for the first time in our lives, have a function of more than one independent variable. We can take derivatives of it. It's called multivariable calculus. Woohoo! So I'm going to tell you, if you have a normal function, and again, if I go fast, I apologize, play the video slower, see it again, whatever, see the other video, and also I'll upload this PDF, of course. But remember, if you have a single valued function, if y equals a function of x, then it may sound stupid, but I think it also sounds true and correct to say dy always equals dy dx times dx. Just saying an infinitesimal rise of a given single valued function is equal to the derivative times an infinitesimal run, because derivative is the rate at which we get rise per run. So if you want to know how high a function goes, you just move over a little bit and multiply by its derivative, and you'll find out how high it goes. That's not supposed to be a revelation. It's just a funky way of writing derivative. Well, similarly, if you have a variable y that depends on two variables, say x and t, the amount that y goes up, the amount any bit of your metal goes up, the infinitesimal rise in your metal is the sum of how much it goes up per time multiplied by time, plus how much it independently goes up per horizontal space multiplied by horizontal space, right? It's the sum of two rates of change. Each of those rates of change we call a partial derivative, and we write in that funky way with like these backward sixes, okay? A partial derivative is a derivative of a dependent variable with respect to one of its independent variables, while we hold all the other variables constant, just like you did in lab 3. A partial derivative, like the partial derivative of y with respect to x, asks, what is the rate at which y goes up per every bit of x, assuming we don't change t, and vice versa, exactly what we did in lab 3, the graphs and everything. So, and similarly, partial y, partial t is how much y are we getting for every bit of moment of time if we just look at one unit of space, right? Now, the way you compute these partial derivatives is exactly as it sounds. You take a derivative of a function, treating all variables as constants, except for the one that you're looking at. So for example, let's do this, and I know we have 8 minutes. Let's do this. We're going to take partial derivatives of our cosine function for our collection of phase staggered oscillators. So we have y equals a cosine omega t plus kx. There's two variables here, t and x. We're going to look at the rate at which each one changes. We're going to look at the rate at which y changes with respect to each one of these, just like you did in lab 3. So we're first going to look at the partial y, partial t. That means I'm just going to take a normal derivative of y, normal rules, all the same, but I'm going to treat x as a constant, like you did in the lab. I'm going to pretend that x is just another number, and that doesn't change. So the derivative of a constant is always 0, right? So if I take the first derivative of y with the first partial derivative of y with respect to t, I get negative a omega sine omega t plus kx. In other words, the omega came out from chain rule because I'm treating t as the variable, but nothing happened to the kx. This is all back to that exercise in homework 2, like where we did like cosine of omega t plus 3.5 or something. And the 3.5, that raw number, didn't come out. Kx, even though x is a variable, for the moment in our mind, we're holding it fixed, just like you did with the graphs in lab 3. We're holding x fixed, so we're treating it as a constant, so it doesn't come out from chain rule, only omega does. So then if I take the second partial derivative, omega comes out again, the sign flips to a cosine, and I get negative a omega squared cosine of omega t plus kx. Okay, what I've just showed you is how you take the second partial derivative of y with respect to t. I'm treating t as the variable, and I'm holding x constant. On the next, that's why it says x equals x naught, just holding x constant in my mind. I could go to the next page and do the same thing for x, right? I'm going to do the same thing. Now I'm going to treat x as the variable. I'm going to hold t constant in my mind. So if I take a derivative, then x is the variable. So k now comes out from chain rule. K comes out. Omega is now doesn't, because t is now a constant in my mind. And this is a mathematical procedure. It's called taking a partial derivative. It's a feature of multivariable calculus, because we now, for the first time ever, because physics has brought us to our first multivariable function. I am not assuming that you have ever done this before. I am showing it to you right now, because that's what physics is bringing us to. Honestly, I'm not assuming that you know multivariable calculus. I'm showing you multivariable calculus because physics is forcing us to do that. And that's how do you think it got invented in the first place? Because of a physics need. So now I take a second derivative, a second partial derivative. The second partial derivative of y with respect to x, again, treats x as the variable. It treats t as the constant. So from chain rule, k comes out again. The sign turns into a cosine, and we get negative a k squared cosine omega t plus kx. Okay, and now at the bottom of the page, oh, sorry, this should be, so then, oh no, so I did that. Then at the bottom of the page, I just reminded you of what we had on the previous page, where we did a time derivative, where we did the time derivative of the function. So now we got these two different second partial derivatives, a time derivative and a space derivative. They look very, very similar. I think I can relate them to each other because they both have that cosine chunk in it, which is identical. So I'm going to rewrite each of them in terms of the cosine chunk. I'm going to rewrite, I'm going to divide both sides, in effect. I'm going to divide both sides by negative a constant squared. So I can get the cosine thing by itself. So when I do the first one, I get cosine of blah equals time derivative over negative a omega squared. And then I do it to the other, I say the same cosine thing equals space derivative over negative a k squared. Okay, I'm almost done. I'm almost there. Why am I doing this? Because now I can set them equal to each other, because equals, things that are equal to equals are equal, or whatever. Each one of these is equal to cosine, so I set them equal to each other. So I write the time derivative over a omega squared equals the space derivative over a negative a k squared. I could divide both sides by a, I could divide both sides by -1, so the a's and -1 cancel out. So now I have, and then I multiply both sides by omega squared. So what I get in this big black writing in the middle of the page is I get second partial derivative of y with respect to t equals constant times second partial derivative of y with respect to x. I get time derivative, second time derivative of y equals constant times second space derivative of y. That's what I get. That is another differential equation. It's another second order differential equation. It happens to be a partial differential equation, but it looks very, very similar to our one and only other differential equation. Look at the bottom, our old differential equation that the whole rest of your exam is all about is second derivative of y with respect to t is directly proportional to y itself. That's a mass going back and forth on a spring. The bottom equation written in brown is the differential equation for an oscillator. It says the acceleration of a mass on a spring, it says the acceleration of a mass on a spring is directly proportional to how far away the mass is from equilibrium. A mass will accelerate back home at a rate that's proportional to how far away it is from home. That's what oscillation, restoring force, is. This wave equation looks shockingly similar to that. The left side is the same. The middle part is another constant proportionality. The only difference is this one says that if you look at a big, long string between you and your partner, if you look at a big wave, you look at a piece of that string, it's saying the rate at which a piece of that long string, if there's wave pulses propagating back and forth on the string, a piece of that string will accelerate back home to the equilibrium axis at a rate that is directly proportional to the concavity of the string at that point. Where did I get concavity? We'll look at the right side. The right side of this equation doesn't just say y, it says second derivative of y with respect to x. First derivative of y with respect to x is called slope, like as in the slope of the string. Second derivative is concavity. What does concavity mean? How bent, how curved, how much like a bowl it is, how unflat it is. So an oscillator accelerates to the home position at a rate that's directly proportional to how far away it is from that position. A wave pulse accelerates back home to its home orientation at a rate that's directly proportional to how bent or disturbed or perturbed or deformed or distorted or concave it is away from that orientation. A point will accelerate back to flatness at a rate that's directly proportional to how unflat things are at that point. The bigger the bump, the faster it'll fall down into flatness. That's what a wave is. If that equation is true for every single point in time and space for anything that is a wave, and anything that is a wave must follow that equation. That is the second order partial differential equation for waves. And it came from building up a collection of phase staggered oscillators. Last thing, that proportionality constant, omega over k, is just a fancy way of saying, or omega over k squared is a fancy way of saying speed, because omega is cycles per time, k is cycles per space. So cycles per time over cycles per space equals space per time for cycles. So acceleration, this is my last minute, I'm done. A piece will accelerate toward equilibrium axis at a rate that's directly proportional to the concavity from that axis. And the constant of proportionality is the square of the rate of flow, the speed at which this wave ultimately propagates across the x-axis. It's a remarkable equation. There's a lot of information packed in it. I'm not saying you have to say all of that in your question 4, but that is all coming from question 4. Okay, that's enough for now. If you have, I'll stay if there's any questions, but that's it. We got to the end. If you have any questions, I'll stay, but if not, I will see you in 2 days. Come with questions about the practice exam in 2 days, please, and I'll answer them. Okay, but thank you very much. Yes, have a great day. Have a great day. Awesome.
Bye, Professor. Thank you.
Thank you.
Have a good day, Professor.
Great. Thank you. You too. Have a great. Thank you. Thank you.
I do have a question.
Yes, I'm going to stop.